Alrighty, what we're going to do is we're going to evaluate this double integral here. But first, before we do that, we have to change the order of integration. Now, why is that? Because if you look at this guy right here, this y to the third plus, just looking at this as a indefinite integral, and you try to integrate with y, there is no closed form solution, meaning that there is no solution that can be written in terms of elementary functions, combination elementary functions. We can't use the u sub or whatever. It's not happening. I guess. I don't know for sure because I haven't particularly studied this function, but there's some, I don't know how people proved it, but some cannot be integrated. So what we're going to do is hopefully what we're going to do is not just hopefully, we're going to integrate this with respect to x. And when we integrate with respect to x, then we're going to get x times this constant, and we're going to evaluate at the endpoints. But we need to change the order of integration, which means we have to deal with these bounds here. Now, the thing is let's write down what d is. So we're integrating on these bounds, and those bounds give us d. So d is equal to xy such that, as we see the outside dx, 0 to 1, so x is between 0 and 1. And then y, on the other hand, is between these bounds, radical x and 1. And notice that the region D has nothing to do with what our function is there that we're integrating, or integrand, I guess. That has nothing to do with it. It only has to do with these bounds. So you could have a totally different function and still have that same D. And so this right here means the function is y equals radical x and y equals 1. And I think because that's something I can draw easily, I'm going to. So we, there's situations where something's, really difficult to draw and I don't draw it, but if it's easy, I think I can do it. I mean, I can do y equals square root of x without much pain, there it is. And then y equals 1 is a horizontal line. And then x is between 0 and 1. So we're going to have 0, 0, and 1, 0 right here. So, okay, mistake. It's more like, I would call that a typo. It's not like I really made a typo there. Okay. So what is the region we're looking for? I drew this sort of larger picture, but in fact, the region we're looking for is just this piece right there. So what we have is that on the bottom is square root of x, and the top is y equals 1. This is a type 1 region because I have a function above and a function below. But what I want to do is I want to rewrite this, and I don't think I necessarily have to do a new picture, but since I have this, since I can do it on the iPad, I'll just do it that way. I'll just write a new one. Oh, why don't I zoom in too, just to make it even better. Oh, I don't know if it's better, but anyway, okay. So let's make a type 2. When I make a type 2, what I do is I reverse this and not make this a top minus bottom, but a right minus left. So you see y equals square root of x is the same thing as x equals y squared. And then this vertical line right here is x equals 0. So what I have now is I have a function on the right, and I have a function on the left. And so for a type 2, if I were to, so, okay, let's just keep going on this. So for type 2, I have d equals all xy such that, as we see, this is the point 0, 1. So y is between 0 and 1, and x is on the left 0 and the right y squared. And so we've recast this as a type 2 region, and in both cases these are D, and that is definitely the trick for us. Let's go ahead and write down the integral then. So the integral, so this integral is going to equal this double integral square root of y to the third plus 1. Okay, now I'm going to integrate first with respect to x equals 0, x equals y squared. So that's dx. And then dy with y equals 0 and y equals 1. And now the idea is that I'm going to be able to integrate this sort of easily. So that was the hard work. Okay, so who has a question on that? Okay, so let's go ahead and integrate. It's not like super neat, but I could convert this into typed math. It's sort of cool if I did that. But okay, so see, this part here is a constant with respect to x. So when I integrate this, I'm going to get, okay, still 0 to 1, but I have square root of y to the third plus 1, and the antiderivative with respect to x is, I mean, this is just a constant, maybe times 1, and antiderivative of 1 is x. So this is going to be times x, and x goes from 0 to y squared, and then dy. Okay, so then I have 0 to 1 radical y to the third plus 1 times y squared minus 0 dy. 0 to 1 y squared y to the third plus 1 to the 1/2. Why am I taking that big step of writing this as to the half power? Because I'm going to integrate. How do you integrate this? What method are we going to use? All right, use substitution. I'm going to use this. It's a very classic use substitution problem. I'm going to use the technique from all the major calculus books in, their math books. I don't know, in America, I don't know what other people are doing, except I've seen some stuff on the internet, which I think is, okay, whatever. I'm just going to tell you that some people are learning it a different way than I think you should be doing it. All right, so I'm going to take the derivative of u, and that's du, and then for y to the third power, it's 3y squared dy. Here's the part that I have a problem with. You are not supposed to divide both sides by 3y squared. It's technically incorrect. You just divide both sides by 3. Because we only have the integral dy. So if you have dy, if you put in u, anyway, I'm just going to do it that way. We can talk about that later, and maybe even I'll discuss it with some other people, what they think. So anyway, let's just do this one right here. So we have, yeah, maybe that statement's not right. So maybe think through, but I'm not going to do it that way. Okay, so this dy, as we see, is 1/3 du. And this, sorry, it's all going in the right place, but let me just, if I feel like it, I can do y to the third plus 1 to the 1/2 y squared dy. And so this right here, as I can see, is 1/3 du. And then this part here is u. Another way also is you could multiply by 3 and divide by 3 and have 3y squared is 3y squared is du. You could just put a 3 there and divide by 3. So this is going to give us the integral of u to the 1/2 times 1/3 du. I'm also going to change the bounds. When x equals 0, we see that u is going to equal 0 to the third plus 1, which is 1. And, oops, okay, this is not the right place here. So I'm going to put 1 here. When x equals 1, u equals 1 to the third plus 1, which is equal to 2. And now I have 1/3. The antiderivative of u to the 1/2 is u to the 3/2. Divide by 3/2. Evaluate from 1 to 2. So we're going to have 1/3 times 2/3. 2 to the 3/2 minus 1 to the 3/2. So this is going to give 2. 2 to 3/2 is 2 rad 2 minus 1. And we did it. I mean, the hard part was setting up. The use substitution should be a fairly simple thing to do. And that was That was 15.2, number 53. Oh, sorry, everybody. At the very end, I made a mistake. I don't know what. That was dumb. I don't even know if it's dumb. It's just careless. 3 times 3 is 9, so it's obviously 2 nines. Okay. Wow, that's so, like, how come I was doing it was all coming out all right? And any questions about that? So we're gonna have to do some, use substitution and integration by parts. And so, anyway, might as well get going on that. Okay. Hey guys, just wanted to point out that one of my students said, why did you multiply 3 by 3 and not get 9? I wrote down, I think I said the word 9, but I wrote down 2. This is the,
You did.
okay, well,
That's why I didn't.
okay, so anyway, it's 2 ninths, not 2 over 2. So anyway, all right, there we go.
Maybe we
Bye, everyone.